Hey everyone, today what we're going to talk about is this idea of connecting a battery to something that's going to use that energy or that voltage in a circuit. So you can see here's our normal setup of a battery, a switch, and a light bulb. And if I wanted to redraw this without having to draw the actual light bulb and the battery, we can shrink down that schematic to this. Remember we said that the battery was two lines, the positive terminal being longer than the negative terminal. The switch in this picture now is closed, so when we have the switch closed, current is allowed to flow because there is an electric field in the wire pushing charges through the wires. When they hit the light bulb, we can draw them like this with the squiggle lines. That represents some resistance to the flow of current, or like we saw the bottleneck in the first couple labs. And when the charges start to pile up on either side of that resistor, with it resisting the flow of charge, we know that heat is going to be given off, and if that object gets hot enough, it could give off light. So in the case of a light bulb, the resistor here is the filament itself. The filament gets so hot it burns and glows and gives us visible light, and then you go back around through the circuit. The reason that battery was written with that little E is because we call batteries or generators a source of EMF, which we call electromotive forces. They provide us constant potential differences or constant voltages. So down the bottom picture, it's like that person lifting those marbles up that pegboard. So that is you doing work against the field, giving those marbles higher potential. As they start to flow down to lower potential, they encounter all those pegs. So that would be like the resistance in a wire, and it would slow down the charges, and the charges would have to give off energy. So the batteries are these sources of EMF, these electromotive forces coming from the chemical reaction, raising the charges from low potential to high potential, or in the case of electrons, just doing the reverse. It's a charge escalator or a charge pump. We've tried to come up with many different ways to explain how the charges separate and maintain this electromotive force. So you might see it written as EMF, or they might just write the potential or the voltage right next to your schematic. So in here they wrote EMF. If you ever see that in a problem, just know they're giving you what the battery's potential is. So going back to this demonstration we talked about today, we want to have one battery. We have a couple amp meters here. We have one before the light bulb and one after the light bulb. And the question was, what are these amp meters going to read? So if we have these two amp meters here, they're going to measure the amount of flow through the circuit. We could see that amp meter 1 reads a higher current. We could see amp meter 2 reading a higher current, or we could see them both have the same amount of current flowing through them. And you can make arguments for each of these. For amp meter 1, since the charges leave the positive terminal and head towards the light bulb, as they do that, they're going to go through the first amp meter, they're going to get used up in the light bulb, and then there'll be nothing left over for amp meter 2. So that's one way you could say that the first amp meter has a higher current value. Some people said that the second amp meter has the higher current because really electrons are what's moving, not positive charges. Since electrons are moving, you'll see the second amp meter actually read higher than the first. And the third argument here is that we're not talking about the charge being used up, we're talking about the energy being used up when we say that the light bulb lights and uses the energy from the battery. That's the difference between voltage and current. Remember, voltage is the energy per charge, whereas the amps is the amount of charge that flows by every second, so the rate at which charge flows. You've got three arguments there that, yes, they could be the same because all that's happening is charge is flowing through the first amp meter, through the light bulb, and then through the second amp meter. And all that's being used up is the voltage or the energy. So you've got those three options. Let's see what actually happens. And what you're seeing here is that current is the motion of charge. It's the amount of current passing through any section of this wire does remain the same. So what goes through the first ammeter goes through the light bulb and then comes back out that light bulb, returning to the battery. The charge is not used up. You can't create or destroy the charge. All you can do is transfer it around. What is used up is the energy, and that energy creates an electric field that pushes the charges through the wires. So what leaves the battery and returns to the battery are the charges. If you want to say it's the flow of positive charge, fine. You can say that the positive charges leave the positive terminal, go through everything, and return to the negative terminal. And if you want to say, yes, really electrons are mobile, then electrons go the reverse direction, head through the light bulb, and return to the positive terminal of the battery. In either case, it doesn't matter. The light bulb will see moving charges that have high energies because of those electric fields and give off that energy in the form of heat and light. So what we got out of today's lab was Ohm's law. We said that as current passes through wires or through resistors, energy is lost, and that potential difference comes from the charges moving from point A to point B across a wire or across a resistor. So we said that we've come up with this relationship that current is proportional to voltage. We saw that if we increase the voltage, we're going to increase the flow through that device, but it's also inversely proportional to what we call R, which is our resistance to the current flow. If I want to rearrange this formula, we could say that voltage is equal to current multiplied by resistance. And if I want to solve for what resistance is, we know voltage is measured in volts. The voltage is measured in volts, current is measured in amps, so resistance would be a volt per amp, which is a joule per coulomb per second, which gets really, really crazy. So because Ohm is the one that found this empirical law, we use ohms as our resistance unit. So ohmic devices have constant resistances, and there's a potential drop as the current flows across them. So the graph on the left here is what we saw in the lab. As we increase the voltage through a resistor, the current increases as well, and that's due to the constant nature of that device. Devices that have nice steady slopes we call ohmic devices, and the light bulb, if you look at that slope, the slope you can still see follows the V equals IR, but it does curve up. So non-ohmic devices, their resistance changes depending on how much energy you put through them. But if you take the average at any point, you can still apply Ohm's law. So Ohm's law is not a law like Newton's law that is universal and goes everywhere. We call it an empirical law that satisfies our observations and hypotheses, but again, we don't know if this is used everywhere. So the slope of a voltage versus current graph gives us resistance. What about the area under that curve? Slope gives us one thing, area can be just as important here. So if I look at that area under the curve, I'm going to look at just the units. Volts, remember, are joules per coulomb, and the current is measured in coulombs per second. So if I get rid of the coulomb, I get joules per second, which, if we remember back to mechanics, this is the amount of watts. And what we measured in watts was the amount of power that was delivered to an object, in this case, the amount of power that's delivered to our devices. So as charges move through the wire, they experience a drop in potential. Their potential energy is going to turn into something, heat, sound, light. So energy is QV, provided by the battery. The change in energy per second is U divided by T. So what we could do then is say charge times voltage divided by time equals our power. Charge per second here is the current. So you could take the current times the voltage to give us the amount of power that you've delivered. If the device stays on and is at a constant voltage, you'll get a constant current, so you can just write power as IV. It doesn't have to be 1/2 IV like the area we saw on the last. Say you didn't know the current running through your system, but you knew the voltage and you knew a resistor. Well, now that we know Ohm's law, we can say that V equals IR, and if I don't know the current, I can sub in what current is into my equation. And so another way to write power is V squared over R. So if you know the voltage provided by the electromotive force and you know the resistance of your light bulb or whatever device you're dealing with, you don't need the current and you can get the power rating just the same. Just to make sure that these units work out, remember this is volts squared, and I'm dividing that by resistance, which is amps over volts. So I can get rid of one of my volts, and a volts times amps again gives us wattage or power. And of course, just like we did for capacitors, If I didn't know the voltage, but I knew the current and the resistance, what I could do is put voltage into my equation and get one more power equation that says that power is I squared times R. And again, check the units on that to see if you get a power rating as well. So we have 3 power equations here that all can be used to tell you how many watts of power are either delivered to your circuit through the battery, how much energy is lost in a wire or in a resistor, and from that power rating, we know how many joules per second are released. Like in a 100-watt light bulb. A 100-watt light bulb tells me that there's 100 joules of energy that leave every single second. Okay, so that doesn't seem like much. 100 joules of energy leaving a device every single second. So then why do your parents get so bent out of shape when you leave the lights on? Well, the power companies don't charge you for wattage. What they charge you is something called kilowatt hours. And a kilowatts are just a measure of joules per second, and we can multiply or convert hours into seconds. So if I do that, I could have kilojoules per second multiplied by the conversion of hours to seconds. You see that I'm actually getting the amount of energy. So the power company wants to know how much energy you're using, and to do that, you take the power rating of a device, multiply by the time that device is running, and that will actually give you the amount of energy used or lost in that device while it runs. So okay, use a 100-watt light bulb. That's 0.1 kilowatts. That's not a lot, and let's let it run for 1 day. Times 24 hours, you're at 2.4 kilowatt hours. Not kilowatts per hour, but kilowatts times hours. So you think, okay, 2.4 kilowatt hours. What's the big deal? Well, the power company is going to charge you 10 cents per kilowatt hour. So running that one light bulb all day, leaving that light bulb on all day long, you are going to be charged 24 cents for leaving that one light bulb on. But that's not the reason your parents get bent out of shape. That's not the only thing that is being powered in your house. There's refrigerators, there's air conditioners, there's many things that you're plugging in, your TVs, your computers, your phones, that are getting power delivered to them, and the longer they are plugged in and the longer they are running, the more energy you need to use. So if you ever go look at that meter outside your house, the faster it's spinning, the faster you are using energy in your house. So that's Ohm's law, and that is a way we can calculate the power rating through different devices in your circuit. Use these equations to solve some problems, and we'll talk next time.